哎，hello，hello，
看啥？
啊，
你要看看啥？
差不多要开始上课，你们呢？上一班？
嗯，
哦，
下个，
下课
嗯
，OK，OK，OK，
先，对咯，
啊，你们上我课哦？
是，
哦，time series，
对，
上 MA 耶，
嗯，
不错，
我已经习惯是折磨。
嗯，OK，OK，OK，
解锁，提起通话筒。
嗯，OK，maybe we left some administrative announcement to later when more people come. We'll start the class first. Okay, where should we start? Okay, maybe let's finish up the discussion on limit first, and then we will continue with continuity that we introduced last day. Yesterday about sequential continuity. So the last piece of limit that I want to tell you is about lim sup and lim pim. Anyone heard about these two things here? Lim sup and lim pim. You know? What do you know about it?
I know limit.
Huh? What?
I know limit.
You know limit.
Yes.
Yeah, lim sup. Yeah.
X approaching to infinity is limit of x approaching to infinity supremum supremum with the condition y is greater than or equal to x. Something like this.
Okay.
You
Okay.
need to write out for me.
Sure. Okay. Okay. Sure. Sure. Okay. So we're gonna have two sequences. Okay. Out of one sequence, we're gonna build two sequences. Okay? We're gonna build two sequences. So these are the two sequences we're looking at. So let's given a sequence. That. So we're gonna build two sequences. So one is Bn, one is Cn. Okay, so what is Bn here? So Bn here we'll define using inf of ak such that k is greater than n. Okay. Or what we meant is you look at the set of ak and then you just restrict to those terms that is greater than n. Does this make sense? But what is B1 here? For B1 here, you need to look at A1 up to A infinity, to A very big, and then find it. Okay, and then B2, you look for A2 up to infinity, and then find the infinity. Okay. So can you imagine this Bn is it increasing or decreasing? Increasing or decreasing? What's the relation between B1 and B2? Can you imagine? So every time, right, you remove one sequence, one term in the sequence, and then you pick the largest one. Right, you remove and then the smallest one. The greatest lower bound, sorry. Greatest lower bound. Can you imagine? 不懂我在讲什么。
你可以给他们看这个第二个，给他们就
OK， 我可以给，but then like 要先学一下听懂的东西，听不懂。OK，OK，听不懂是，so OK。I think the hardest part to teach these courses, right, is like how to make the extracting visualize. Okay, so imagine, right, you got a sequence. Imagine any sequence that you like. Okay, so out of this sequence, maybe you can think of it as bounded below first. Bounded below. Okay, imagine. Okay, and then you find the increment. Greatest lower bound. Okay. Well, I mean, like you can think of this example, right? Eh, 不要开15分钟就抛弃我了，再等多20分钟可以吗？每天进步一点。以前我也是这样，我听了5分钟我的老师的课不是我抛弃他，是我大脑抛弃的。我想听，但是我听不进。But then like slowly up to third year，慢慢我可以抓到45分钟，老师在讲什么东西。But then 还有15分钟没事，一直到现在才比较 OK， 听得懂人家在讲，对吗？对吧？先保持5分钟的定力先，好吧？我们5分钟后再说。OK， so look at this， 来慧姐，给我一个 sequence， sequence 什么意思？给我一个 sequence， sequence 什么意思？快点，旁边翻开一下。How about N 啊？OK， how about N？ 我可以选 N 吗？因为1 over N 有一点 OK， 好吧，我们先玩 OK， 我喜欢 对，我民主，对，我是假民主，我是伪民主。OK， 我只是想要从你嘴巴讲出我要你讲的东西吧。OK 啊，选1 over N 啊，给你1 over N。来，慧姐，来1 over N，1 over N 来了。OK， 1 over N 来了。Okay, so can you figure out what is B1 here? B1. So what is B1? So write down the definition. Okay. So increment of A1, A2, A3, A4, A5, A6. So what's the increment of this one by N? What's the increment? 什么是 increment？ 快点，旁边跟他讲呀，快点跟他讲。Greatest lower bound. Lower bound 什么 ？lower bound 很多字要懂哦。什么？可以给我一个 lower bound 吗？这边先给我一个先。 -1 is the lower bound because -1 is less than or equal to all the numbers you choose here. But then what's the greatest lower bound? Because if you choose negative 0.5的话，也是个 lower bound，对不对？全部都大过0，全部都对吗？并且对吧？再给我一个 lower bound，再给我一个，随便给一个号码不了，先不用想什么，然后再跟你讲对错。你是会解啊？会解，我要会解。再给一个 lower bound，另外一个0 ，very good，听取别人的建议。0为什么是个 lower bound？来跟我讲，为什么？它符合什么条件？来，旁边跟讲。0是小于等于所有的event。OK， 所以这个就是 lower bound。OK， 小于等于所有的 term。OK， and then in this case here, increment is the greatest lower bound. How do you show? You need to show by definition 哦，就是说any number that's greater than 0 is not a lower bound. Okay, because why 呢？如果你有一个 epsilon greater than n, Archimedean, so okay, so any epsilon greater than 0 is not the lower bound of an because by Archimedean property there exists a n such that 1 over n is less than 0. Okay, and then this 1 over n here will live inside is one of the an. Yep. It's one of the terms, one of the sequence terms. OK 吗？你是 lower bound 里面最大的意思是什么？再比它大一点就不是 lower bound 了，明白？这句话也明白它 greatest lower bound 它是最大的，再比它大一点点，它就不是 lower bound，因为你找到那个 sequence 里面有一个 term 比它小，对吧？记不了英文，记一下华语。Yeah. So maybe one challenging part I come back and teach. Maybe it's a language problem. 至少啊，你毕业啊，都要把这个概念带回家，可以传给你的孩子。考试写不出来不用紧，反正这个概念你要学会。OK 吗 ？Yeah. OK. Okay. So right. So B1 here is 0. Okay. Later you'll see why I don't like this example. Okay. Okay. So how about B2? How about B2? Ah, also 0. Why? 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 I remove what? I know, not like that. So what did I remove here? If I look at B2, I just look at all the A, K, and K variables, so meaning I remove the first term. But then you still have something that approaching 0. Okay, you still have this thing happening here. You still have the greatest lower bound to be 0. This proof doesn't change. Okay, so it's 0. B3, eh? What did you remove for B3? A1 and A2. But then you still have this phenomenon occur here. So you get 0 here. Okay, so actually, what you produce from here is this sequence Bn here is a constant sequence. Okay, and then turns out that this matches up with the limit of this sequence actually. Okay, this is what I said. This is so good because I'm gonna put how about 1 over n? Okay, so I listened to you already, right? You should listen to me now. Okay, so how about 1 over n? Okay, how about n? So let's choose a prime n equals to n. Okay, so here 1, 2, 3, right? Okay, so in this case, maybe I can test one of you lah. In this case, what is B1? 文伟啊，文伟是不是？喝水的那个叫文伟的。文伟 ，OK， 来 ，what is B1 prime? Infimum. The infimum of this sequence here. 1. Okay, very good. 1. Okay. So do you know how to show it's 1? Because the minimum is 1. So minimum exists, minimum will be equal to the then like the maximum case. Maximum exists, then maximum is the supremum. Okay, how about B2 prime? Maybe Pingjie. Sorry? Yeah, I throw away the first term. Then I look from second term to second. You still look for the infimum. Yes, that's right. Huh? One minute? I remove this one of whole sequence. I remove A1 and then I look at the sequence starting from A2.
But A1 still in, or is look at start from A2.
I start from A2. Then A2, right? So A2 is 2. Okay. Okay, and so on. So you can see that this sequence will create a new sequence, but then in this case, it's the same sequence. Okay, in this case, we will do kind of a duality here. So I also can define Cn as a soup of AK, where K varies with n. So instead of looking for the greatest lower bound, we're looking for the lowest upper bound. Okay, the soup. Okay, maybe in this case, we can look at the Huijie examples again. Okay, in this example, what is C1? What do you think? What is C1 here? Sihu, you want to try? What is C1? Supremum. Don't want. Typically, the answer is cannot be don't want. Seriously. 有一个学生哦，他东湾在我的 general topology 过后哦，他成绩是这样的。真的不好说。真的。try to answer. Okay, try to answer. Wow, very good. 你看，一中就对了，是不是很好？勇敢一点。错就怕，错也是，反正你就是来错的。Okay, so C1 is 1. Why? Because this is a maximum. Right? If maximum exists, then it will be a supremum. Then C2. C2. And 一兴要 try 我已经讲了，答案不可以是不要的啊。讲出来正经，讲出来了。他比把在动态。Yeah, sure. So you remove A1, right? You remove A1 and then you find what's the maximum. Let's find the supremum. If you cannot find maximum, you find supremum. And then sort of. So in this case, actually Cn equals to An. Where is Cn equals to An? Right. Good. Okay. So good. Okay. In that case, we're going to define what is a lim sup and lim it. So we're going to define lim sup An to be the limit an n to infinity of sup of the sequence we're looking at just now. Okay, and then a lim in, and should be the limit of the increment sequence that we get just now. Okay, maybe you are first hand. I should write. Let me see. Okay, let me rewrite this. So there's a bracket, maybe looking something like this, so that you don't confuse. Okay. But this one is an operator. Okay, then this one is operator. Sequence. Okay. Very funny, very funny here. This new operator here, right, is defined using the usual operator you know on the use. So that's why we put a yes. There's name for it. This is a limit supremum or upper limit or limit superior. Yeah, or this one is limit inferior, limit infimum or lower limit. Okay, these are the name for these things. Okay. Very good examples here. Let me see. Okay, so maybe we can go back to this examples again. Okay, so we see that B1 0 and then C1, Cn are actually An. Okay, so what's the limit of Cn and Bn? Can you see or not? What's the limit for both of these? What's the limit? These two sequences. What's the limit of the constant zero function sequence? The limit. 0, 0, 0, 0, 0. So what's the limit? 0. Okay. And here, 1, 1 over 2, 1 over 3, 1, but and converge to when? 0. Okay, so you can see that these two limit of these two sequence is the same. Not only the same, it's equal to the original limit. Okay. Okay, so this is the phenomenon I want you to observe here. So, so our goal is to show that theorem. Okay, our goal is to show that a limit of a sequence is L if and only if the lim sup and lim inf are all equals to L. Okay. Lim sup and lim inf are equal to L. This is our goal. Okay, so this is our goal. Right. Maybe I can motivate you this statement with one more examples. Okay, look at the 1 and -1 example. The alternating -1 sequence here. Okay. Maybe you can ask what's the Bn and Cn here. What are the Bn, Cn here? What do you think? Why? 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 How do you see that? Okay, so if you are looking for infimum, right? So if you look at the infimum between 1 and -1, right? Who is the greatest lower bound? Or who is the minimum? -1, right? Okay, so no matter you remove 1 or remove -1, the -1 still exists. Supremum also, no matter you remove 1 or -1, 1 still exists. Okay, so actually the increment sequence you will get -1, and then the supremum sequence you get 1. Okay. So you can see that if you take the limit of these two, right, are they the same or not? Are they the same? Not the same, huh? Okay. Not the same. So that's why this matches up with our conclusion last time, right? This sequence doesn't have limit. This sequence doesn't have limit. Okay, so the lim sup should be somewhere here, and then lim inf should be somewhere here. Okay, they're separate. But then these are perfectly good convergent subsequence. Orthogonal Rousseau says what? If you have a sequence that is lying in between some closed rounded interval, right? So the closed rounded interval here you can take -1 to 1. That is a convergent subsequence. So these are the convergent subsequence. Okay. Two possibilities. Okay, these are convergent subsequence. Right, good. Good so far, okay. But before that, maybe we need to introduce one more property on lim inf and lim sup. So maybe I invite you to think about this first before I proving it. So if you manage to find lim inf of an and lim sup of an, so given two number, right? What are the possibilities? Hypotomy law, right? Okay. Less than, greater, or equal to. So what's the relation between these two numbers? What do you think? Which one is greater? I just now tell you that they could be equal, right? So this is one of the possibilities. So how about the rest? Which one is greater? Could be. So, okay. Usually people will guess, right? Sup could be greater. Because when you take sup, it's already greater. Okay, so now what we're going to show is even if you take limit, this limit of this sup is still greater or equal. Okay, so it cannot somehow go below the limit of limit. Obviously cannot go below limit, but then it cannot, the limit also cannot go below. Okay, so how to prove this? So let's prove this. Okay, prove this. So first of all, okay, we already know that the infimum should be less than the supremum. Okay, one is lower bound, one is upper bound, right? So this has to be true. Okay, now we need to settle the case for limit. How do we prove for limits in this case here? What's our goal here? Our goal is very important. If you cannot write out the goal, then pretty much you are scam. When I write down this limit here, right, what does it mean? What does this mean? When I write down limit of something, what does that mean? Converge. Right? So that means the sequence converge to this two number. This two number is the limit of some sequence. Okay. One of them is a inf of an where n greater than k. The other one is sup of an when n greater to k. Sorry, k greater equals to n. Right. Good. So let's break into cases now. So if lim sup of an is infinity, then basically we are done. Okay, so then we are done. Because any number should be less than or equal to infinity. Okay. If on the other hand, lim inf is infinity, what can happen? Can anything greater equal to infinity? Huh? Why? Yeah, very good. So, very good, very good. So then we claim that lim sup is also infinity. Why? Because for every m in R, okay, what does it mean by lim inf is infinity? That means there exists an n in n such that this m will be smaller than the inf of an. Okay. If this one need to go to infinity, this term here must always greater than all any m you can pick. But then this term here might depend on which n you pick up. Does it make sense? Okay. You need to imagine a picture always when you go to infinity. This is the prototype you need to remember. So this guy go to infinity, right? Okay. So no matter what m you pick, there will be an n such that all the terms beyond it will be greater than this. So if you move this m up, there will be someone greater than it so that it can go to it. Okay. Okay. So m less than if, and then, but then we know from first statement that we know that inf is always less than or equals to sup. Okay, so we also have sup that is always greater than a real number. So sup also level to infinity. Okay. Good. Good. Okay. So in that case, we'll suppose both of them are finite now. Okay, then we'll show that they are less than. Okay. Sure. Okay, so now suppose lim inf is L and then lim sup is M. Okay, for some LM in. All right. So what do we do now? So what do you do now? We try to show that. So we want to show that L is less than or equals to M. Like that. Okay. Or maybe you can show that L minus M is less than or equal to 0. Or last time we mentioned that, what did we mention? Let me see. Okay, never mind. I think this is okay. Then we show that L minus M. Or actually, you can show that for every epsilon greater than 0, L minus M should be strictly less than epsilon. Okay. Slowly push toward things that needs epsilon. Okay. Any idea? Minimum of LM. What do you mean? Mean?
Yes.
Mean? LM like that.
And use stuff to minus. Like.
What stuff?
Divided by.
Okay, okay. So I mean like I need this difference, right? So I need to compute this difference. But what's your assumption here? What's your assumption? What's your assumption? What's your assumption here? What's your assumption? Assumption? What's your assumption here? What's about L and M? Huh? Limit, right? Limit of certain sequence, right? Okay, so you know that inf of k greater than n of k. Right. Convert to L and then sup k greater than n of a k converge to M like that. Okay, or that means if you take this difference, you can bound by some epsilon, right? For all epsilon. Okay, and then there exists some n. Okay, let's say this is NL, epsilon n, such that this is true, and such that for ON greater or equals to NL, this is true. Then the other one, there's another n that make this epsilon true. Okay. Okay. Yeah, so you see, you got these two things, and then you got this L minus M to find. So, what trick we get there here? So, what trick we can play here? So, you want from here, get here, right? But this one, yeah, somehow get somewhere here, right? But then to get this thing, you need to introduce these things in.好，想一下，假设考试宿舍题怎么办？怎么办？这个考试宿舍题。老师交白卷给你了。好，你说用 increment 小于等于 supremum？ Yeah, sure. 对 but then like L minus M here doesn't contain these two terms yet, right? So you need to somehow introduce them. 你要 supremum 先 Okay, let's try. So let's say L minus M. Yeah, supremum. Yeah, supremum like that. Answer. Okay. And then why do we want to do this?
那左边那属于就是小那个一体嘛。
So you mean you want to have so okay. So is the inf of AK. Okay. And less than equals to sup. And then 用这个做什么意思？
那 supremum 再加一个 infimum 减 infimum，然后那个 supremum 可以直接 cover 掉，因为它那个 epsilon 大过这个，是吗？
没有，我要做模现在。我要做模，现在我要做。What do I do next? What do I do next? 清闲要做模。
negative
你是这样 OK
negative 数就用 smaller in negative
对 smaller than
然后
等下我应该要转方向啊，这个要转去这个
就smaller than 然后只是把那个 negative 数变成是negative
yeah sure but then in that case I
然后再通过那个 definition
这样我不是要转过来了
要跑
我不是要转过来了对吧？这样对吗？是不是这样讲？
应该是 smaller 的
啊？
应该是 smaller 的
哇
我做 negative 我不是要手啊，then negative 数为什么大于等于是小于原来小于等于？你算的你讲 negative one 也不是小于等于大于等于啊？就是一开始是 increment 小于数啊，然后 negative 数就会小于那个 if
哦，OK，哦，对，OK，Thank you，对，没有错，OK，good，and then OK，
然后 L minus C 会小于
最小的 epsilon。So you group these two terms together. Right. Okay. And then you try to make these two maybe to be less than epsilon over 2. Then you can get epsilon. Can we do that? Yeah, that's the point. So in this case, what can you do here? So maybe you can pick. So from here, maybe you can fix epsilon greater than 0. So you pick epsilon over 2 such that these difference bound by epsilon over 2, then you can get this one. Okay. Does it make sense? 可以吗？有问题吗？还是对于这个有问题吗？怎么这个是反方向的？有没有人问这一个？为什么是方向是反的？这个，不然我抓一个来问问。啊，为什么方向是反的？我也可以帮我把 S 个图。凯泽，来，没有办法会找到。来，为什么方向反的话是可以用 S 个图？你不知道？不知道就写一写，把这个写出来。这个是什么意思？这个 absolute value，I think like 我们的 quiz 有考 right？这个 inf a k k greater than n minus l imply 这个小于 epsilon over 2大于 negative epsilon over 2 right？OK，but then 如果你 introduce 这个 minus sign 进去，有差吗？这边右边加了，那边右边减。OK 吗？可是那这样子，懂我讲吗？就是你 introduce negative to both sides，then what do you get? You also should switch your sign to get this. OK 吗？可以吗？所以它们是相同的。OK，agree 吗？我放 negative to 上边。OK 吗？OK，yeah. Another thing about this is, you should think of this absolute value is just taking a distance, not displacement. 懂 distance 跟 displacement 的概念吗？你不懂？你有拿 physics 吗？OK，你忘记罢了。OK，很好。So distance is 你跟它距离多少吧？我不问你是往前走还是往后走。Displacement 的话，我会知道，比如说我往前2步，或者往后2步，我就要 negative。而 displacement is come with direction，distance 是没有 direction。OK，so 这个 absolute value 是没有 direction。不管你是拿大的减小的，小的减大的减小。That's why it is positive. That's why 我们 define absolute value to be positive 的，给它 positive，negative 的话就把它变回 positive，对吧？或者 negative term 来或者 negative two。Make sense? OK。然后我也用这个 algebra show 给你看 ，actually it makes sense。OK，good。good。很好，有问题吗？Any question so far? Question? question. Any questions so far? 有问题吗？没有。Okay, so I think throughout this week, a lot of technique is you have to cleverly like read some extra term for you to use so that you can use your assumption. Okay, 你要 introduce 一些term 出来 but this term is like you are adding a zero, right? Okay. 不知道你们有没有玩过那个三国杀？玩过吗？
今天晚上，今天晚上。
今天晚上，下次我带个卡牌了。没有人玩过三国杀这边？哦，只有你吧，一个人吧，一个人吧，哦，两个人吧。三国杀哦，你知道有一个卡牌哦，有一个 action card 哦，叫做无中生有吗？有吗？无中生有是做什么？
又玩过模两个，
哦，又有科目了。哎，所以你看，这两过后出两张，出两个出来了。OK，无中生有。OK，看，是吧？无中生有啊，这个。
跟你讲，从这就我就直接生一个薯片。
不可以，那个会 GG 了，那个真的是无中生有了呢。OK，你可以生一个零啊，你不可以生其他东西啊，只有零可以生嘛。Right. Okay, good. Then should we prove this theorem? Maybe I left for exercise for this one. Yeah. So this proof is very similar to what we prove here, but with different epsilon you need to pick. But then it's the same technique. Okay, so maybe I left this for exercise. I try and do this. This is very interesting. Yeah, a very good exercise to show whether you know about limit and range. And this is very easy exercise. Okay, any questions so far? Any question? Maybe I show you one direction is easier. Maybe this right to left is easy. You know why? Squeeze theorem, yes. Okay, because you can squeeze your AN in between inf and sup. Okay, but you know that in the sup, you mean at this L equal to L by squeeze theorem AN. Okay, but in the other direction, you need to use the epsilon definition. Okay, very good exercise. Like similar to what I did in this proof here. Okay, similar to this proof. Okay. Before we end, I mean end this section, I want to like call upon this person. I think now it's like lecture 11 already, right? Week 5. Lecture 11. So I guess so these people where's Bai Han here or not? Bai Han. Not here. I think I'll send email or message. 很易 here, right? Yeah. 陈玉呢? 陈玉 also here. 洪杰 not here. 洪杰 here. Okay, good. 俊汉呢? 陈伟 not here. Okay. So all of you should submit some draft by this week. Okay. This week. And then I think Hen Yu is almost done already, right? You just need some polish, right? Can you like submit soon so that they can have some sample to see? Yeah, I think you are almost done already. Yeah. Also, Chen Yu, I think you still have to put in the proof, right? Yeah. Okay. So for this person, please submit your revision assignment by this week. Okay, by this week. And then so next up will be Seng Yang and Yushen. Hopefully we will get Chen Yu one first so that you have an idea what to do. And then because Hui Jie complained my handwriting is very bad, right? Hopefully this assignment can help you guys to do revision. 没有，开玩笑。Okay. Yeah. So hopefully this revision assignment can help you to do help you to understand my concept better. Right. I think they see your version, right?
No.
Actuals. Huh? I think I showed their A1. No, sorry. I showed the. I mean, like,
Actually, that A1 also contains part of many dots, so we can show them precisely.
yeah, I mean, sure. I mean, like. So actually, before I designed this revision assignment, right, what I asked them to do is I asked them to type out my lecture notes, but not every one of them. And then they don't get score even. So they are doing like charity. There's a yeah, I don't know. Yeah, so basically this notes right is when I was teaching A1, they helped me to type out. Part of it is MS stuff actually. So secretly, right, the few axiom I told you, right, is actually some ring theory, actually. Yeah. But then I think it's very important. Yeah, they also type it out. Yeah, this is what they did. Okay. I'm not purposely or intentionally trying to show it to you because I want you to type out what you understand about this course. Because what you write, what you say, right, is what you think. If you write very simple, that means you think very simple. So I will get you like, what's wrong with you? I mean, like, what's lacking of you? You understand? So if I have a template to give you, right, you just follow. You don't know what you are doing, and you are just following. So I want you to start from zero. And I want to see what's in your brain so that I can somehow get you, or maybe I'm missing something, for example. I didn't tell you, then I will know. You understand what I said? So sometimes I don't want to give too concrete template because I want you to understand what I say. And I want to understand what you think. I want to see what you present. Okay, but there's template everywhere already if you go and find it. Yeah, everywhere. Okay. Yeah. Oh, another thing I want to advertise for my link here, right? There's a link I put on here is the link game. Did you see the link game? Link. Did you see it? That I put here. Maybe it's time to talk about it because we already talked about the number, piano axiom and set theory. Okay, this link game is very fun to play. I don't not really fun, but then the point is, it will train you to use definition. Maybe there's some setting that you need to learn how to play this game, but then the thing that they test you here, right, is exactly what we are learning. Okay, should we do some example? Let's see. Do we have any example? Shit. I change setting to play everything. Or maybe a regular, non-regular. And maybe you can show that addition is associative, right? Try to show that addition is associative, and then you try to use the induction to prove it. Then this one will guide you step by step. It's exactly the step that we write down in our lecture notes. Okay. You want to go back and try? Go back and try this. Can train your argument. Okay, because if your argument start, the game won't let you continue. Okay, can try and play this. Okay, it's very good. Yeah, they have piano axiom. They have set theory. Okay, both of them. It's very relevant. Another thing is, I think we need to set our midterm exam. Okay, so do you want to do it in week 7 or week 8? So now it's week 5. Week 7 is 2 more weeks. Sorry, tomorrow? No, impossible. I haven't printed out your exam sheet yet.
week 7, scope, yeah.
Yeah. Yeah, so yeah, definitely, yeah.
After chapter,
I guess I will confirm again, but definitely just until maybe epsilon delta definition of continuity. That's it.
Wow, that was awesome.
I think around week 5 of 10. Around week 5 of 10. So you want week 7 or week 8? Because you want week 7. Oh, you got another week. Okay. Week 7. Week 7? Week 7? So week 7, do you guys want to do Monday or Friday? I think Monday we have to do 1 to 3, right? And then Friday we can do what time free on Friday? Maybe 2 to 4? 2 to 4. Okay, so you want Monday or Friday? Huh? Friday? Friday? Monday or Friday? Sorry? Friday, 2 Friday, Friday, 3 Friday. I think Friday, mostly. Okay, then we fix when week 7 Friday 2 to 4 after tutorial. So you can also ask questions during tutorial. Yeah, if you have more revision questions, then we can settle in tutorials. Yeah. Okay. 2 to 4. So I'll go and book a room because if you look at this classroom, the table is very small. So I try to get the proper table for you. I realized that I think today we got more chairs. Is it? Feel like we got more chairs. Just less people. Less people. Okay, in that case, I will start the attendance and then we can take a break until 1:07. Let's see if I can start attendance. Okay, you can try signing now. Heng 怎么你们全部昨天没有在呢？哦，OK，天嘞，
李老师，你们不要叫我把头发。
他没有讲他睡觉，有点累，因为看到有点累的梗，是有点累吗？还是我很累？应该是我很累那个。再看一下。
哇嘞！给这个词的，我嘞，我嘞，我嘞，我嘞，
没有人看过这个梗没？没有看过？
哦，你们不知道？你们认识 Joe Bro 吗？Joe Bro 不认识，Joe Bro 是不认识。哦，你们在家真的是读数学吗？对不对？
觉得可能吗？
啊，这样啊，这个都
我觉得那你是不是大家他天天在打？
是，因为他最近才去想的，
但是你开始有点沉迷网络。
确实，每个晚上都要打。
没有看过这个。
他是点播点才子，还有一个
假的，对我的耳朵好一点。
他声音很难听啊。
有人睡觉的时候，有人睡觉的时候你放开。然后别的好像他管的还是咖啡，后来就直接这样上过来，大家看评论区全都是怪不得。倒是，但是我们那个时候你要跳这个舞，啊，跳舞，啊，真的瞬间不累。你在后面打配吗？啊，你在后面做配？配音的话，
所以也要唱那个。
我这个配唱啊，你要跳。中途就这样。原来是这个样子。不要站起来。写的完全听说，写的鸟会吃那个假学生。这边是可能，是不知道为什么男的呢？先外国人我在聊一下那里面有个场子来啊，比较有类似中原有题，中原题的点头。那个 我就小学来就不负责，给就负责。必须得我建议就在不属性教育哦，这个。一起这个是然后接下来是
你下个星期
我是下个星期的3D 会。
你们卡了这种，
都你没有来，到底是多方面？
这个礼拜的 quiz 就是 midterm 的范围啊，差不多
没有啊，就前个
多少钱？
就是每一个前面的几个月啊，对啊，week 6考嘛，就 week 5的东西。Okay. Okay, let's continue with sequential continuity. Maybe calculus 1, you see continuity epsilon delta before. So later we will show equivalences between these two. But we're going to start with sequential continuity so that we will link the sorry? Yeah. So we will link the limit of the sequence, okay, to the limit of your function. Okay, yeah. Right. So anyone can recall what's the definition of a function being continuous? You cannot run away from epsilon. So anything you have to start with epsilon. Yeah, epsilon. Sorry, not epsilon. Okay. The epsilon is hiding. Okay, it's hiding inside the definition. But then you need to talk about some convergent first.
Functions.
What do you mean? Oh, sorry. Continuous. Okay, if for every sequence, okay, Sn good, that converge to x, okay, we want fxn also converge to fx or x? Fx, okay. X doesn't make much sense. Okay, so we converge to fx. Okay, good. So yesterday we looked at one examples, right? We look at these examples here. So let f be a function from this closed border interval R defined piecewisely x and x minus half, where for x in between 0 and half, we get x, and then for x in between half and 1, we get x minus half. So the picture looks something like this. Okay, so yesterday we proved that f is not continuous at x equals to half. Now we're going to prove that it is continuous at everywhere other than half. Okay, so to prove not continuous, right, you just need to pick a convergent sequence to half, and then show that that FSN that you produce does not converge to F half. Okay. Okay, how about continuity here? Okay, so continuity is show for all these points other than all these points other than. So from this picture, actually, your function split into two. One is before half, one is after. So we're gonna do that as well. So we'll split. So today we're gonna prove the second part. Proof number 2. Yesterday we proved the first part. So proof 2. So we split into 2 cases. Split into 2 cases. One is p greater than half and p less than half. Okay, later you'll see why we split into 2 cases. Okay, so case 1. Well, we need to take an arbitrary sequence, right? Take an arbitrary sequence Sn that converge to a point that's greater than half first. Okay, so then we want to show that Fxn converge to P. Right. Okay. So, well, how to do here? Think about it first. Spend a minute. So you need to write down what this means. Okay, write down what this means. So here epsilon comes in again. So that is for any epsilon greater than 0, there exists some n epsilon in n, such that for all n greater than n epsilon, we have the absolute value of Fsn minus Fp should be less than epsilon. Okay. But you know what is Fp, right? Do you know what is Fp here? When p greater than half. What is Fp? One. Is it one? So when p greater than half, right? It is p minus half. It is p minus half. It is p minus half. So you can slowly unravel what are these. So now by definition, this is p minus half. So in this case here, you can replace this guy with Fsn minus p minus half. Like that. Okay. So far so good. Okay. So how on earth you're gonna achieve this? Think a bit, think a bit. So you need to somehow bring this Fsn back to Sn because your assumption is on this any sequence. So, but how to go back to Sn, right? So you define F using S. Okay. So, but then there are two parts here. There are two parts here. One is X minus. So, which one you're going to use then? Which one are you going to use? X minus y.
Oh, because P greater than.
Okay. But then you can imagine some of your sequence are maybe start here. It's start here. No need. Okay, so maybe I need to draw out what I'm trying to say here. So your P is around here, right? But your sequence maybe jump around here. So maybe some of your fx is x. Some of your fx is x minus 1. But the point here is the limit of this sequence is P. So for large enough n, your sequence should live somewhere around P that avoid half less than half. You know why? You know why? Do you still remember the epsilon thing? Epsilon. Sorry? You can pick n epsilon. I can pick n epsilon, but then it depends on the epsilon I pick, right? So I can pick my epsilon to be away from half. I can pick my epsilon away from half. Right. So that for all n greater or equals to this epsilon, all my term will live inside this epsilon string. Avoid half. Do you know what epsilon I should pick? What epsilon I should pick here? What epsilon I can pick here? P minus half. Is it enough? P minus half. P minus half enough or not? My epsilon is strictly less than, right? Okay, enough. I think it's strictly less than. My definition is strictly less than. Okay, strictly less than. Equal or strictly less than? Do you know what I'm talking about? So either you want to include this line, or you want to avoid this line here. So I want to avoid this point, right? This point, use which one to define, sir? Let me check first. Yeah, okay, that's fine. Because half is using the second one to define, so doesn't matter. Okay. Epsilon over half, epsilon equals to P minus half is okay. Okay. Or you want to use half times P minus half of n. This avoid. Okay, cool. Good. So in this case here, take epsilon greater than 0. Okay, and then actually I need to pick one epsilon first. So let's call this epsilon NP such that the sequence for xn will converge. And then I also pick epsilon. So this epsilon is what Taylor suggested, right? Take P minus half. Okay, let's call this in n such that n greater than equals to n epsilon. And of P minus half, then I get Sn minus P less than epsilon. Okay. Okay, So the first part here is I want to make sure the conversion of this Sn minus p here. The second one is I want to make sure the convergence. I want to make sure the convergence happen after half. Okay. So maybe let me write down. So here is the conversion of xn to p, and this one is to make sure the conversion happens after x equals to half. Okay, does it make sense? You will team. Okay, later I'll show you why we do this. Then we can choose n epsilon equals to the maximum of these two. Such that for O n greater than this n epsilon here, we can finally compute this guy. Okay, fsn minus fp. But just now we know that fp is just p minus half. But then I told you that fsn has two possibilities, right? Either x minus half. But then with this conversion after x equals to half, meaning all my xn will live after half. So meaning I just use the second definition of my piece, right? So this fsn will evaluate to Sn minus half. Okay, so 来会解帮我加这个东西，这加起来是什么？对，加一下，这整串一下，加一下，这整串，看到吗？加一下 ，Sn 减 P 而已吗？对不对 ？Okay, so you can see that miraculously this half will disappear. You just get Sn minus P. Then this Sn minus P is exactly the conversion that you can see there. Okay, so we can bound this Sn minus P by epsilon. It's exactly what you wanted. Okay, so you use the conversion of this Sn to show the conversion of Sn. Okay, does that make sense? Yeah. Yeah. Okay, so case 2 is similar. Case 2 here become P instead of P minus half. Then you need to do something like this to make sure that your convergence happen before half instead of after. Okay, so how to control? You need to pick a different epsilon to control your sequence. And this epsilon is still arbitrary, because this is the conversion for your sequence. And then second, you need to control your convergence based on your piecewise definition. Then you can fix to one part of it. Otherwise, you need to jump into x minus 1. Okay, any questions so far? 有问题吗？有问题吗？ Okay. Do you understand why I need to pick 2n here? There are 2n to consider here. 拼接 why? Yeah. Yes. Not continuous. It's just to avoid the other definition of it. Okay. But if you imagine, if I go to the other side, right? Sn minus P minus half, how to compute? Where do I get the condition for that? 没有啊。I only know how to compute Sn minus P. 我不会 Sn 减 P 减1/2，这1/2是个 extra. It turns out that it can be cancelled from the piecewise definition. You choose nice. OK. 假设里面有这个1/2，这个1/2会不见了。So it turns out that they cancel nice. Okay. Good. Good. Okay. Right, so there are few continuous function. Maybe I don't show it in class. If you have question, maybe we can do it in tutorial. Yeah. Otherwise, you can choose it for presentation during the tutorial. I'm not sure it's this week or next week. We're doing continuity. For example, identity function is continuous. Okay, very easy. This one is the easiest proof you can see because it's almost flowing through the definition. Okay, because fx equals to x almost doing nothing. Because fsn and fp is exactly the sn going. It's the same. Okay, so if you have conversion in the domain, you must have conversion on the codomain. Actually, they are the same line. You notice this domain and this codomain is the same line. 同一条线来的，有注意到？懂我在讲什么吧？这两条是同一条线的，这两条啊是同一条线，相信我吗？啊，相信我吗？这两条是同一条线。那同一条线来的，那它是同一条线来的。Yeah, they are the same line.
你翻新
Topologically the same.
哦 ，OK，
They are the same line. 我第一堂课不是已经跟你讲了很多个 same 咩 Sometimes I try to be imprecise. Sometimes I try to be precise.
I cannot understand.
If you don't understand, right, you should come and take topology. It's not. It's okay. It's okay. You just believe it is the same. Then next time I'll tell you why are they the same.
How simple? How simple?
Okay, how same? Topology I already told you already. Topology is the same. Okay.
Y equals x squared also the same as a straight line now.
Y equals to?
X squared the
Actually, it's the same.
So according to the definition, that's the same line.
Actually, it's the same. Okay, doesn't matter. Okay. Actually, it's the same. Okay. So actually, they are the same. In this case, exact same line. It's just we plot it in a different place.
Link by exact same.
The image of F. Yeah, image of F. Yes. Okay. I try to be not precise with this thing, but then I want you to believe that. Okay. Yeah. Right. Because if you show this continuity, it's exactly following from your assumption. When you take sequence x and p, what is fxn to fp? It's really the same. It's really the same. S square, almost the same. Why is it not exactly the same? Because you need to care about the speed of your function and the curve. If you learn calculus before, the speed x squared is faster. But then it's still a line. It's still the same. It's still the same line, but you move faster. It's still the same line, you move faster. So the curvature there, right, represent the speed actually. But still a line. Yeah, still a line. Because your domain, your codomain is just a line. Where your codomain is just a line. Where your codomain is you cannot run from other places. And then another thing is this function is bijective, right? So you can go back and forth. S squared is not. S squared is okay. Another thing is absolute value. Absolute value is continuous. Yeah, it's continuous. Very good exercise to try and do this. Okay, this is a very good exercise. You should do it. Well, yeah, this is a very good exercise. Basically, you split into 3 parts to show. You can see that there are 3 kinds of calculations. And then this anyone recognize this? What am I doing here? This is a piecewise function of
It's the symbol Q1.
yes, rational number. So you send it to minus x if it is in the rational number. If it's rational number, you send it to x. Okay. So which line represent rational? Which line represent irrational? What do you think?
What binding? For line.
There are two dash line, right?
Oh, that's fine.
Yeah. If not, there are infinitesimal in many line. Up to you lah. Yeah. Okay. Okay. So fx equal to x something look like this, right? Okay. So why do I become dash line here? Because I only take value for irrational. So the rational one doesn't have value on this line. But the rational one, where they go? They go to y equals to minus x. So these are the irrational. Okay. So that's why the negative irrational become positive irrational. The positive irrational become the negative irrational. Okay. So here irrational and irrational. Okay. So the claim is f is discontinuous everywhere except at 0. Okay, at 0 still continuous. Hey, does this challenge you about the drawing line one? How do you? This is just the top, right? Okay, you can try to show that it's continuous only at 0. Okay, try and do this. Very fun. And try and show that it's not continuous. Okay, maybe I test you. Maybe I didn't tell you how to find this sequence that works. But what do you need to show? You have to show this continuous at a point that is not at 0. Jinhan, maybe Jinhan try. How do you show a function is not continuous at the point? Huh? Okay, okay. Not arbitrary, right? Avoid 0, right? Okay, and then and what do you do? Take what?
You can separate. You can say this.
One certain.
X is rational and X is irrational.
Okay, that depends. That depends. But in general, discontinuity, what do you need to do?
If X is rational, then we have a sequence of irrational functions.
You need to function the value. You need to apply the function. So you apply the function to the sequence that approach to the point, but then fx that doesn't approach to f. So there are two sequences there you need to consider. One sequence is converging in the domain, the other sequence is converging in the column. Okay, there are two sequences there. Okay, don't confuse with the two sequences. So you take a sequence that converges in the domain, and then you apply and see how it converges. Okay? Does that make sense? Okay. Yeah. Okay. Okay. And then how about this one? Okay, this function here. This function. So you take for all irrational, you just take the denominator part. Okay, 1 over n. And then for irrational, you send it. Okay, so how can you imagine this picture here? So maybe you got like the half, right? 1/3, right? 2/3, right? Okay, or 2 over 3, right? 2 over 3, 1 over 3, these go to the same n value. Okay, same height. Okay, so the height is determined by the 1 over n. Okay, the height of the rational. Okay. Maybe you can ask like, what are these red block, right? This red block, rational numbers. Yeah, these red block are rational numbers, but the highest one, do you know what's this? What are these guys?
Breakdown.
Huh?
The highest one is breakdown.
Yeah, represent what number? What number give you the highest top here? What's the height? This height should be 1. Okay, so these are the integer. Okay, negative 1 over 1, 0 over 1, 2 over 1, 3 over 1. And so 1 is the height. And then your height should be decreasing, right? When you look at more rational numbers here. It's decreasing, right? So how about this? How about this? the second highest one. You know what are these? What's this type? Maybe you have to guess.
Non-integer half integer.
What's this type then? I told you the highest one is 1, right? How about the second one? What's the second one? This one is 1. How about the second layer? Second layer is what? What's the value? What do you think? Yeah, see what their relative position from -1 to 0, for example. 1/2, right? Okay, so here are the 1/2. What's the next one? 1/2. What's the next one? 3/2, 5/2, 6, 7/2. Right. Okay, so these are the 5/2, and then 1/3, 1/4, 1/5, 1/6, 1/7, like that. Yeah. Okay, so this function, what do you think? Where does it continuous? So you can show that actually it's continuous at every irrational number, but discontinuous at every rational. Do you have an idea why is it easier in the irrational case? Because in the irrational case, you will just always get 0. Okay. Okay. Yeah. Okay, you can try and show this. Their answer here. Yeah. So I think these are the exotic. Okay. Right. Okay. Maybe some picture for you to see. Some picture for you to see. Okay. So what do we mean by sequential convergence here? Okay. So this is one kind of example. Okay. You look at this function here. And this is your function. And then maybe you pick some sequence in your xn. Maybe like this. Take it this way. So you take 1 point here, 1 point here, 1 point here.
And then you convert to this key.
For this x is p. To write p. Okay. And then out of these points, right? Out of these points, go and check what are their f value. Okay, you can also plot up the sequence. Okay. So if this function is continuous at p, and then this function Sn converges to p, that means Fsn also have to converge to f. Right, so this is a schematic presentation of the definition. Can明白我讲什么？听我讲吗？
大概这样来。
上海再看，有其他的，听我再看哦。For every xn that converts to p, Fsn also have to converge to f. So this is the two sequence the definition of sequential quantity. Okay. So for every, right, this is just one of it. So you can pick any other. Maybe you can pick one that just going down like that. Also can. And then your function here will going down like that as well. Okay. Does it make sense? Okay. Let me see. How about discontinuity? Let's see what happened for discontinuous case. So if you look at this function that we show in first case, right, it's not continuous at this point, right? So let's say I pick this function like this. Okay, this is the sequence that converts to p. And then I look at the Fsn. You can see that this Fsn doesn't converge to anywhere. Okay, and then this Fsn kind of like speed up. 没有像刚才一样会连在一起，上面有一点，下面有一点，这边有一点，这边有一点。Can realize? So I purposely draw this color to show you that the green part here is actually evaluated to this bottom. Okay, and then the purple part here evaluated to the upper. Okay, so you go through this green part, and then you split off, go up. and then go down again, and then go up again, go down again, go up again, go down again, go up again. Like that. Okay, so from here you didn't see any limit, right? Because they are not converging. It's diverging. Okay, and if 可以想象 Okay, and so this is a discontinuous exponent. Okay. Yeah, any questions so far? Any question? For the examples that I show you, right, I really highly recommend you to try out the proof. Okay, to try out the proof to yourself that at which point they are continuous and discontinuous. Okay, yeah, very important to test your that understanding. Okay, if no problem, then we will continue with the property of continuous function. Okay, so actually similar to limit law, right? We also have very similar continuity law. So suppose f and g function on domain A, okay, which are continuous at P. Then we can know that f plus g is also continuous at P. And a scalar multiple of f is continuous at P for any scalar. And the product of them is also continuous. What's the next one? You want to guess? Good. But then what condition you need to impose here? As long as at the point is not zero, we are okay already. Okay, because we just need to check at this point. For the rest, whether it's defined or not very important. But if it is non-zero here, actually you can show that maybe around neighborhood. Okay. Okay. Right. So what do we need to do? Maybe I show you one, then you will know what happened here. Why is it very similar to limit law? Okay, so let's write down proof of one first. So what do you want to show? F plus G is continuous, right? P, so what does that mean? So that is for every sequence that converge to P, I want to check that F plus G on that sequence also converge to F plus G on K. Okay, but then what's the definition of F plus G here? Did I told you or have you learned anywhere else? It is just evaluating this function point-wise and then add them together. This is by definition. Okay, and then the other place is just FP plus GP. Okay. Right. Does this look familiar? Familiar. Okay, maybe we need to unravel one more time. So what is this arrow means? For every epsilon greater than 0, there exists a n epsilon in n such that for all n greater than n epsilon, fxn plus gxn minus fp plus gp is less than epsilon. Hey, this one familiar or no? This one. Not familiar. Not familiar? Not familiar? Okay, let's go back. Limit law. 怎样？可以啊，你没有用过啊？它可以搜我的 handwriting 的。它可以搜我 handwriting 的。Yeah. So you see, this limit law, right? AN converge to L, BN converge to L, AN plus N converge to L plus N. Just now the AN we are looking at is FXN. BN is BXN. We have FXN converge to GBN converge to M. Why? Because they are continuous. Okay, so you can just use limit law. So that's why you have like very similar property of limit law. You see, sum, scalar multiple, product, and quotient. Okay, so exactly the continuity is just conversion of sequence. That's the same thing. It's just we put it as a function. Where we view it as a function of this. Does that make sense? Okay. Okay, so you can think of continuity as a preserving convergent sequence. OK preserve 的意思就是保护嘛，你要保护它嘛。说保护的意思是什么？这个人还在嘛，对吧？他还在，你才能够保护得了他。So preserving continuity means what? If it's continuous at first, you preserve it, it's still continuous. I mean, yeah, sure. Okay, sorry. I should say preserving convergence. Continuity, you should think of it as preserving convergence. So previously you are converging. After you apply F, still converge. 可以吗？明白吗？明白我讲过吗 ？Hello, guys, girls, boys and girls. Okay. So what is continuity? Preserving what? Preserve what? Convergence. Okay, for every convergence sequence, you apply F, continuous function F, is still convergent. Still converge. 对吗？是不是这个定义？回去。Here, see, the function is continuous if you start with a convergent sequence, you apply F, still converge. 导致的就是 continuous 的定义。Okay, make sense? Okay, so this convergence don't disappear. Okay, if it's disappearing, then it's not. Okay, good. So in this case here, this theorem comes from limit law. Okay, try and write them down in full. So in this case here, from here, I can say that polynomial functions are continuous functions. Why? You know what is polynomial function? What's polynomial function?
The sum of x to the power.
Oh, okay. So polynomial function.
所以你用 finite number of addition 和 finite number of multiplication 和 finite number of scalars 还有一个 variable 来支撑。
Okay, very good. So maybe I can write in this way. So it's a sum, is a finite sum from 0 to n of a scalar times a power of x. M power of x. Okay, like that. Okay, so I claim that this is continuous. Why? Each of them is continuous. So you need to tell me why each of them is continuous. Well, each of them looks like what? So for example, like C0 plus C1x plus C2x squared, C3x squared. Right? So let's say each of them continuous. So if each of them continuous, the sum of them continuous. But then why each of them continuous? Each of them looks like what? X, product of x, and scalar multiple, right? Okay, so we know that I show it to you, right? Fx equals to x is continuous, right? So the product of them should be continuous, right? Product of them should be continuous. Let's say like this, and then the scalar multiple is also continuous. But then this is a bit. This is C0, there's no x here. Is this continuous? Why? Why? Huh? Why is this continuous? Huh? 一行 line。try，不要紧，我不会扣你分啊。C0 is what kind of function? Constant 咯 ，constant function continuous 什么？I think 我们没有在班上学过哈。Constant function continuous 什么？啊 ，constant function continuous 什么 ？Why 呢 ？For every xn converge to x, what is fxn? It's just p. What is fx? Still p. P have to converge to p. Okay, constant function p converge to p. Okay, does it make sense? 更容易学啊，你都不用，你都这个 function 根本就是constant function， 它肯定 converge to 还是 fx 也是 p。Okay, so constant function is continuous. So polynomial function is continuous. Okay, good. Yeah, I think maybe before we finish, one more thing is square root. You can try and show that exercise square root function is continuous. Okay, square root function is continuous. Hey, do you know square root function is defined where? Where is it defined? It's not on the whole real line. It's just defined from the positive half, non-negative half, right? From 0 to infinity. Okay. Maybe two cases you can do lah. One cases is p equal to 0. The other cases maybe p greater than 0. Yeah. Okay, and then there's some tricky bound you can check. Okay. 什么？
我原是你问，如果那个 x 安放在我就想我为什么不像我讲我喜欢把的那个图片放在那个地方。
Then we have to go to complex analysis. Yeah, it's not real analysis. So I need to go to complex analysis. And we can put negative. Okay. Any other questions? Yeah. Okay. Try and go back and try the exercises. If you're not sure, then you bring to tutorial. Okay. Bring to this week tutorial. We can go through if necessary. Okay. So bring to tutorial. Okay. Then see you tomorrow.